Alright, hello everyone. Today I'm actually going to start with a grind report instead of the problem review, so just so you guys know. And as you can see, today is December 24th, which is Christmas Eve, obviously. And I not only didn't pause my grind for the January contest of USACO, I actually grinded for 10 and a half hours. So that's pretty good. 10.5 hours on Christmas Eve. And so basically what I did today was I finished the 2019 February contest I mocked yesterday, and I got totally traumatized by 2D prefix sum. Painting the barn, I'm pretty sure, is the most classic template 2D prefix sum. I mean, the silver one is, the gold one isn't, but I spent 5 hours to finish the silver plus gold, even after looking at the solutions, because this problem is just traumatizing. There's so many details, especially on the gold version. I think I spent like 3.5 hours on the gold and 1.5 hour on silver, which is way longer than I thought. And then I also finished the dishwashing from the same contest. And then in the afternoon, I mocked the 2021 January contest. And I'm actually pretty excited about this one because my math count coach in middle school, he passed gold, I think, in this contest as a freshman, which is really impressive because freshman in platinum is really impressive. So I mocked this contest, but I only received a score of like pretty low, like less than 700, which is way lower than the 750 promotion line because I got less than 700, like 689, I'm pretty sure. And even that score I got after doing Uttered but Not Heard about like 3 months ago. I already did this one once, and even though I did this problem again within like 30 minutes without looking at the old code, it's still kind of cheating because I did that before, even though 3 months ago. And then the second problem was pretty good. Telephone, I was able to solve most of it. I don't know what bug there was that caused me to not be able to solve the 3 points, but I kind of basically solved it. And I don't think my program's time complexity is actually correct, but it's still 76 milliseconds because after some calculations, it should be 1.25 times 10 to the eighth for the time complexity of my program, but 76 milliseconds is just way too fast. And the last one, I was able to figure out the solution for the first 10 test cases, but there must just have been a bug, so it's disappointing. But anyways, that's the grind report part of today. So as you can see, today's Christmas Eve, and I not only didn't pause my grind, I actually grinded for 10 hours. So that's pretty good. Now, well, I need to log in anyway, so this is good. All right, now comes the problem review part. All right, so the problem we're looking at today is the USACO 2021 January contest gold problem 1 of Uddered but Not Heard. All right, so you can pause video first and look at this problem yourself. All right, asking the rest through the problem. So basically, what you're being asked is you're given a string which means so Mildred, Bessie's cousin, is humming the alphabet over and over, and then Farmer Nodge heard a few letters in the song that she's humming, like which is just several times the alphabet, and then you're trying to determine at least how many times Mildred must have hummed the alphabet in order for Farmer Nodge to hear these letters. So Farmer Nodge doesn't have to necessarily hear every single letter that Mildred hummed, but is he can only hear letters in the right order, right? Obviously. And now the alphabet contains the same letter as the alphabet, but it's in different orders. So they contain the same letter, so each letter can only appear once, but they're in orders like maybe as Mildred and ABC like that, right? And now you're trying to determine for any alphabet at least how many times Mildred must have hummed it for Farmer Nodge to hear these letters. So now you can pause the video first and think about this yourself. All right, I assume you gave this problem a try. So basically, first of all, to solve this problem, we had to make a very important observation, is to notice that if we already know the alphabet, it's actually pretty easy to determine how many times Mildred has hummed it. So let's first assume that the alphabet is equal to the alphabet, right? So it's A, B, C, D, F, G, it's in the right order. And now if we hear this sequence, how many times have the alphabet been hummed? The alphabet, which is the alphabet, been hummed. Actually, we can notice that is just the number of adjacent inversions in this alphabet. What's an adjacent inversion? So an inversion is when a later letter appears before an earlier letter in this string that we have here. And an adjacent inversion is when I is appears later in the alphabet than I plus 1, which D and B is an adjacent inversion, and then B and A is another adjacent inversion, and then C and A is another adjacent inversion, right? We can notice that the number of adjacent inversions plus 1 is going to be how many times Mildred has at least hummed the alphabet if it's in the right order like this. Because think about it. So why, first of all, why is it plus 1? Because we have to hum the first time the alphabet, and once we have an adjacent inversion, we have to hum it a second time, right? We have to, because you can't get D and then B because it's not in the right order. So now you have a second time, right? This is the second time, and you hum the third time, and you hum the fourth time. So it's just the number of adjacent inversions, 3 right here, and then plus 1. So now you have 4. You have hummed the alphabet 4 times. And now we made this observation. It makes the problem a lot easier, but it's not entirely just completely solved, because now you also have to notice that this is DP. Don't ask me how, because DP, a lot of times you just kind of have to notice it. You just have to know that's DP and then solve it with DP. It's just about doing enough problems and you just know it. So the DP for this problem, notice that there's only 26 letters in the alphabet. And very importantly, no test cases will ever have more than 20 letters. So that makes it perfect for state compression DP, which means we can state compress how many letter have been how many letter in the alphabet have appeared. So basically, now we have a state Fij means when the alphabet contains only the letters in the state I, how, and the last one, the last letter is J, how many times at least we have to hum it. And this is kind of hard to understand, so I'm going to explain it once again. Let me actually use my code this time. So first of all, I solved this problem twice. This one is a code from like a few months ago, and then I solved it again today without looking at the old code. So those two are going to be similar, but not completely the same. I'm more familiar with this one because I just wrote it like 20 minutes ago. So in this code, I only have one dimension for the state. Fi means when the alphabet only contains the letters compressed in this binary number I, how many times Mildred must have at least hummed it. So if you know what state compression is, this number, if you convert it into binary, each digit represents whether a letter is used in the alphabet, and 2 to the 20th power is at most 10 to the 6th power, and this is 2 times 10 to the 6th, so that's the at most what so that's not going to be out of bounds, so we're never going to have a memory exceed. That's why I always set it a bit larger. And now this converted to a binary number represents how many letters in the alphabet is used right now. And now basically how we transfer is for each time we enumerate which letter that already appeared in the alphabet, obviously, that we're enumerating, we enumerate which letter J the alphabet ends with. So what we're saying is the last letter to be added into the alphabet, which now is represented by I, is J. And when this is the case, we just need to find the number of adjacent inversions formed by J and then plus F the alphabet but without J, right? Because we just added J, so that of course this is the alphabet without J, and then TMP is just how many adjacent inversions J formed with every single letter that's already been in the alphabet before we added J. So this is easy to understand. And how do we find TMP? Well, we just have to enumerate every other K that's also in the alphabet, but will obviously appear before J. So for every K, we just add the number of adjacent inversions K formed with J. And we can pre-process that with an env array that we can pre-process it right here. So that's how we solve this problem. And finally, we just output the answer for when the alphabet contains all letters. All right. So this problem, I would say, is kind of difficult because state compression DP obviously is not a simple branch of DP. But if you can realize it's DP and if you can make this important observation of adjacent inversions, I think you'll be fine for this problem. And I solved this 3 months ago, I'm pretty sure, and then I was able to solve it again without looking at my old code about 20 minutes ago. That proves that it's not going to be that hard. All right, I hope this video helped. Thank you so much for watching.